So part 3 of, right? I still don't remember. Lecture 3. And this is going to be about the energy exchanges of changes. Hang on. There we go. So energy drives everything. Chemistry is driven by energy exchanges. Everything exists, it's actually all just energy. And as you get into Chem 1, you'll learn more about this, and it's just awesome. So all chemical and physical changes are driven by energy transfers. Why does water go from a liquid to a solid? How do you get ice cubes? You're removing the heat. So you are removing energy as heat, you're cooling it down, and that makes the liquid go into a solid. Why does it boil? Why does water turn into water vapor? Why does it go into steam? You've added energy as heat to excite the molecules enough where they can actually escape each other and go out. And all that energy you've added gives them the power to disperse and get far apart from each other. We call that a gas. So we often observe this as heat. Not all energy exchange is heat. So here we're actually talking about heat exchange. And we call this enthalpy. Enthalpy is the exchange of heat energy in a system, in a physical or a chemical reaction. Now, it's important to realize the reason our flask here is in a little box, the box represents your surroundings. The flask represents the system. Where does the heat as energy come from? It comes from the surroundings, or it goes into the surroundings. When you take your ice cube tray, and back when we used to use ice cube trays, and you make ice, you put that into a cool environment, the heat from the water goes out into the surroundings, the freezer, enabling the water to cool down to make ice. So the surroundings and the system work together. Your energy is either going into the surroundings, which means it's being released from the system, or it's going, so from the system into the surroundings, it's being released. Or it's going to absorb energy, like if you're boiling water, in which case that heat energy comes from the surrounding and goes into your system. But they're linked. Delta means change. So delta H means the change of energy from start to finish of your reaction. And we consider delta H as the product minus the reactant, or the end minus the beginning. So the energy of heat energy of the end minus the heat energy of the beginning. So we're going to get more into this. So right now, just take it as a concept. If the difference in the heat exchange is negative, then your system is exothermic. That means excess energy was released. So let me go to my whiteboard a minute. Okay, so delta H, our delta H, delta means change. So the change in H in enthalpy is the heat energy of your system, is the enthalpy, and this is measured, all right? This is just, it's measured, you're going to look it up, or you're going to be given it. of the product minus the enthalpy of the reactant. Reactant is your starting material. So a reaction is, the reactants are on this side, the products are on this side. So if my H of my reactant, let's just call this 1. I'm sorry, let's call it 2. I like to use simple numbers for this example. And let's call our final measured heat energy 1. Well, that means my delta H, right? Let's look at that. The H of the product is 1 minus the H of the reactant is 2. I get a -1, don't I? So my delta H is negative. It's a -1, which means energy was released because the heat energy that you end up with is lower. Where did it go? It went out into the surroundings. When something goes out into the surroundings, it's called exothermic. It's exo, it's outward. So delta H is negative, it's exo. All right, well, what about if this took energy? So the measured heat energy, you made steam. So your product is higher than what you started with. This is water, that's steam. Well, this has higher heat energy. Where did it come from? It came from the surroundings. You put it on the stove. The delta H in this case is product, right, minus reactant. So it's a positive number because your ending heat energy is bigger than your beginning. You had to add heat energy for this to have more than this. You had to add it plus heat. Where did that come from? It came from the surroundings. So go back to that box picture. The air around the surroundings put energy into the system. What happens then to the air in the surroundings? Well, you've just removed heat energy from that air, didn't you? The surrounding. So it got cooler. The temperature dropped because you removed heat from the surroundings, it got cooler. So the surroundings get cooler for an endothermic reaction. Now, what about the first time when we gave off heat? Well, that heat went into the surroundings and it got warmer. So in an exothermic reaction, your surroundings get warmer because heat is being released. Because it has to go somewhere. And it goes to, so it's exchanged between your system, which is like your chemical reaction, your little, or your physical reaction, your flask, and the surroundings. So know the signs and why, but if you just use simple numbers like I did, 1s and 2s, to lay it out, if you forget, that'll help fix it in your head. After a while, you'll get comfortable with delta H being negative because it's excess, it's out. Okay. So a phase change, and you do have to know which of these is exothermic and which of these is endothermic. When the heat of the product, the heat energy is lower than what you started, energy was released and it's exothermic. When heat energy in the end result is higher than what you started with, then energy was added from the system, it took it in, it's endothermic. There are some good slides, and this would be a good topic to go look at YouTube and perhaps find some little cartoons or even some images that help you remember the exo endo of each phase change. Okay, I'll go over these tomorrow in actual lecture. So I talked about the melting point and a boiling point and a freezing point. This is the temperature, the single temperature at which this phase change occurs. When the phase change is occurring. As long as there's a combination of solid and liquid, for example, or liquid and gas in your flask, your temperature will not change. It will stay the same until absolutely all of your molecules have changed phase. So you hit the freezing point or the melting point, and your temperature stays unchanging until all of it is converted. Because that energy is going into either releasing the attraction of these molecules to each other, which is what's helping to keep them as a solid or a liquid and letting them go further apart, or cooling them down, removing the energy so they are coming closer together and they can have more interaction with each other, which is why a liquid is close together, disorganized, a solid is close together and organized. It all has to do with the energy levels. That's physical changes. Exo and endo, yes, you have exo and endo chemical changes as well, because every reaction either takes in energy or releases energy. Every single reaction, unless you have the very rare ones that are equal. So I shouldn't say every reaction, but most of them either take in energy or release energy. And some of them require energy to make them happen. So when you have a graph of a reaction, a chemical reaction, you will see it graphed against the energy. Potential energy is your bond energy. That's the energy that's stored in a molecule from the two atoms interacting with each other, that chemical bond. It's storing energy that gets released when that bond is broken. Every single time it gets released. The difference is what gets stored again when you have new molecules, you have a difference there, and that's as far as I'm going to go right now. We'll talk more about that later in the course. But you have these energy charts, and it's important to be able to recognize, it's common sense actually, what the exo looks like and what the endo looks like. Because this is the heat energy of the system, your flask. So if you start out, the left side of the equation, your reactants, has got more energy than what you end up with. It's released heat energy, it's exothermic, and you know this because the product is less than the reactant. And you often will feel that temperature difference, but not always. Just because you don't feel it doesn't mean it didn't happen. It's not always this explosive. Whereas if your starting heat energy is less than your product, it's endothermic. You had to put energy into that reaction from the surroundings for it to be increased. This increase in energy had to come from somewhere. It came from your surroundings. So it came from the surroundings into your flask to make the products have a higher heat energy. So it is endothermic, and often you can detect the difference in the surroundings. As the energy leaves it, it cools down. Okay, so if a chemical reaction occurs and the two feels colder, that means the surroundings lost energy, it went into the chemical reaction, and therefore it was endothermic and it required the heat and input. And it took the heat from the surroundings, and the surroundings, which is your tube, decreased in temperature. All right, so that is the end of part 3. And we will go over all this tomorrow. And I'll show you the video and fun stuff. All right, guys, see you then.